So, welcome everyone to the session 7 of course Microwave Engineering. Um let's get started. As you know, this session is to cover the content, some of the sample numericals from the topic microwave semiconductor devices. So you have come across the video lectures of this particular week, wherein you have seen the different microwave semiconductor devices such as BJT and FET, their characteristics, then pin diodes and control circuits. Then you have also come across some of the diodes and detectors like Schottky, tunnel, gun diode, impact diode, and varactor diode. So these are some of the content, but I have a few questions in mind just to refresh uh, the concepts. So we won't be trying to discuss everything in detail because it's already there in the video lectures. But today's session we'll try to make sure that you got the concepts right. So first question. So I have a few questions like, what do you think? What is your comment on uh, why the PN junction diodes are not suitable at high frequency? Or as you see, you have come across a lot of different types of diodes like pin diode, Schottky diode, tunnel diode. So why this the regular PN junction diode fail at this high frequency? Any comments from the audience? You can even type in the chat. I believe I am still online and I'm audible to all of you. So let me tell you. So this junction capacitance, which is an issue at high frequency. The junction capacitance is very high, due to which the PN junction diodes fail. There is something about the Schottky diode compared to a regular PN junction diode, wherein you have a P type and an N type semiconductors on either sides. We have in case of a Schottky diode, you have something like a metal semiconductor junction. Okay, so here you have a different interface. Rather than two semiconductors, you have a combination of a metal and semiconductor, which is in turn making the capacitance or the junction capacitance to be low. So which is why it is desirable at high frequency. Now coming to something called a pin diode. So what is the speciality of a pin diode? So a pin diode has three layers, wherein the intrinsic layer is like sandwiched in between the P type and N type semiconductors. So that benefits the pin diode by how it benefits by lowering the junction capacitance again. Okay, so that's about pin diode. And the other diode which we came across in this past week content was the varactor diode. So to talk about one of the special feature of varactor diode, unlike the pin and Schottky diodes, the capacitance or the junction capacitance can be varied by varying the bias voltage. So if you change the bias voltage, the depletion layer thickness will vary, then accordingly the junction capacitance will vary. So that is the speciality of a varactor diode. So these are some of the things which I wanted to mention in the beginning. But let's move on to some of the MCQs. I really request you all to put an effort to type in the answers, or you can unmute yourself and say the answers. So, going ahead, the first question is, the classical PN junction diode cannot be used for high frequency applications because of A. High bias voltage, B. High junction capacitance, C. Frequency sensitive, D. High forward biased current. Yes, right answer. As you all said, thank you for answering. Yes, it is because of the high junction capacitance. Now, coming to the second question, Schottky barrier diode is a sophisticated version of the point contact. Is it germanium diode, a silicon crystal diode, gallium arsenide diode? None of the mentioned. So there is a difference from the Schottky diode to a point contact diode. As you know, you have a surface. So basically you have the metal semiconductor junction in a Schottky barrier diode. So it is a sophisticated version. Okay. Instead of the point contact silicon crystal diode. So this is the option B. Okay. So coming to the third question. The advantage of Schottky diode over silicon crystal diode. Is it the presence of minority charge carriers? Or I can say, is there minority charge carrier flow in a Schottky diode? No, there are no minority charge carriers. So advantages, to answer this question, it is not the advantage. So it is a false statement. So then what is the advantage of a Schottky diode? Any guesses? What is the advantage of a Schottky diode? Is there minority charge carrier? Yeah,
Low bit
please.
of degradation layer. There is no degradation layer because of the direct contact between the material. Fast switching times is there. That's why.
Sorry, your voice was little breaking. So I think you answered like there are no minority charge carriers, right?
Yeah.
Yeah, okay. So that's the point. So we don't have the minority charge carriers, due to which the delay is reduced in case of a Schottky diode. So coming to the next question, that is on a tunnel diode. So you're all familiar with the tunnel diode. So the question goes like this, that tunnel diode is a PN junction diode with a doping profile that allows electron tunneling through a narrow energy band gap. True or false? Yes, that's a true statement. So in a tunnel diode, you have a different doping concentration, as you know, which will make the energy band gap narrow, due to which there will be a tunneling of the carriers. Okay, moving on to the next question. Field effect transistors are different from BJTs in that they are monopolar device, bipolar device, bidirectional device, none of them mentioned. So you have come across BJTs and FETs and you know the difference between them. It's very clear. It's monopolar, and you know the meaning of monopolar because there is only one type of charge carriers. That was a very simple question. So, in the beginning of this today's session, we will have a few MCQs just to refresh the concepts, and then later we'll move on to the problem solving. I hope this works. So coming to a question on pin diode, a pin diode consists of how many semiconductor layers? How many semiconductor layers? So all of you know the construction of a pin diode, wherein you have a P junction and N junction, which is separated by an intrinsic layer. So it should be 3 layers. You know what is an intrinsic semiconductor, which is basically a pure semiconductor. And if it is doped with a P-type impurity, then it becomes P. And if it is doped with the N-type impurities, then it becomes an N-type junction. So basically we have 3 layers. Now, coming to the next question, material out of which the pin diode is made of? Yeah. Is there a question? Okay, let me check the chat. Material. Yes. Yeah. So the question is on. I would request everybody to answer this. What is the material of this pin diode? I request everybody to answer. Please make a guess. What is the material of a pin diode? Is it silicon? Is it germanium? Is it gallium arsenide? Okay, let me break it. So it is silicon. Okay, so pin diodes are generally made of silicon. Now, coming to the next question, the behavior of a pin diode is entirely different from normal diodes at all frequency of operation. So, make sure that you understood the question properly. The behavior of a pin diode is different from a normal PN junction diode at all frequencies of operation. Yes, that's a false statement because at till some frequency, say up to some 100 megahertz, the properties of pin diode is as that of a normal diode, after which the behavior is different. At high frequencies, the behavior is different, but at low frequencies, the behavior is same as that of a normal diode. Okay, now let's move on to the next question. Uh, Okay, so the next question is the junction resistance and capacitance of the intrinsic region in a pin diode are connected. Is it parallel? Is it series? I mean, the question is about how this Cj and Rj of which is representing the intrinsic region. So this pin diode has an intrinsic region which will, if you draw the equivalent circuit, this will have the Cj and Rj, the junction resistance and capacitance. So as per the equivalent circuit, are they in parallel? Are they in series? Are they connected across the package capacitance? So these are the options. What do you think? Okay, I have answers parallel. Yes, right. So they are connected in parallel. Okay. Now coming to the next question. I hope you can read the question and give me the answer. It's a simple question. How does the resistance of a pin diode vary with the positive bias voltage? Okay, I am looking at the answers here. So I think the answers are mostly for B, option B, that is decreases. Yes, that's the right option. So as you know, whenever a positive bias voltage is applied, what happens to the RJ? So initially, RJ is of the order of say kilo ohms, so typically of 6 kilo ohm or so, which will reduce to something around ohms, say 5 to 6 ohms or something like that. So, so this is a non-fact. So the resistance of the pin diode, which is the junction resistance, will reduce with the positive bias voltage. Now coming to the next question. Under ideal conditions, when a pin diode is used as a switch, the switch must have insertion loss. So is it a maximum insertion loss? Is it zero insertion loss? Is it average insertion loss? Yes. So I have some answers. I request everyone to answer. So I hope you know what is insertion loss. What is insertion loss? And when we use a pin diode as a switch, so what is the say if it is in an on state, we ideally expect the good operating switch to have a zero insertion loss. Okay, so that is zero. So if it is the off state, it's the maximum, I mean it's the infinity insertion loss, we can say. Okay. Okay, now going to a small numerical. Okay, so this is again based on pin diode. I request you all to just try calculating this. Uh, okay, so let me start. For a shunt configuration switch, the diode impedance is 40 ohm. Okay, so I can write it like ZD. And the terminated line characteristic impedance is Z naught is 50 ohm. What is the insertion loss of the switch? So remember, it's a shunt configuration switch. First you should know how to take the equivalent, and then from that you find out the insertion loss, or you can directly write the expression for the insertion loss. 20 log of 2ZD divided by Z naught plus 2ZD. Please do try to calculate and find the answers for the insertion loss. Yes, so to answer this, so it's 4.2 dB. So please take the insertion loss is so it's a loss and we take it as 4.2 dB. Now coming to the next question, that is a series configuration pin diode switch for which the terminated load impedance. So you have a ZD and then you are terminating in Z0 equal to 50 ohm, and there is the diode impedance value is 60 ohm. What is the insertion loss? So this is a series configuration a pin diode switch. So in case of series configuration, the equation is 2ZD plus Z0 divided by 2ZD. It's not 3. Can you try once again? Yeah, please take this as minus 20. I just missed that minus 20. Sorry, I took it as because it's loss, it's the insertion loss. Yeah, the right option is, not in this, I think, yeah, it's 3.3 dB, approximately 3 dB. Please don't consider these options. Okay, now I have a few questions, few MCQs on varactor diode. Varactor diode is a semiconductor diode in which uh, what can be varied as a function of reverse voltage of the diode. Is it the junction resistance? Is it the junction capacitance? Is it the junction impedance? This is a very simple question. Varactor diode, that is variable reactance. So varying what? By changing the reverse bias voltage, we are changing the depletion layer width, which is basically changing the junction capacitance. Okay, so coming to the next question, the width of the depletion region of a varactor diode, is it increasing with increase in reverse bias? Is it decreasing with increase in reverse bias? Or is it remaining constant? Width of the depletion region. Okay, so I'm not sure if, okay, so this width of the depletion region, with by if you increase the reverse bias voltage, the width of the depletion region will increase. Okay, so if you have larger reverse bias voltage, you have a larger depletion region width. Once if the width is increasing, that is an inverse function, inversely related to the capacitance. So as the width increases, the capacitance will decrease. So that's a relationship between this reverse bias voltage and the capacitance, effective capacitance, and the junction capacitance. Okay, so coming to the next question, the varactor diodes are operated in what region to achieve maximum efficiency possible? Is it the cutoff region? Is it the saturation region? Is it the reverse saturation region? Or is it the active region? Yes, that is the reverse saturation region. So I hope you remember what is the reverse saturation region. So as you know, the region between the reverse saturation point and the point just above the avalanche region. Okay, so the capacitance variation and the reverse voltage swing are limited between these operating region. Okay, okay, now we have a few questions based on gun diodes. Okay, so a few basic questions, maybe you already know that, but just refreshing. Silicon and germanium are they direct gap semiconductors? Are they indirect gap semiconductors, band gap, or indirect band gap? So silicon and germanium both are examples of indirect gap semiconductors. Uh, and you know the reason for gallium arsenide to be used in gun diodes, even that is a related question. So gallium arsenide is a direct band gap semiconductor, and if you see the band gap for silicon and germanium, you all know that this is something around 1.2 electron volt, and this is something around zero point 0.7 electron volt. So this gallium arsenide has much smaller forbidden energy gap, that is which is due to which this is being used in the fabrication of gun diodes. So gallium arsenide is used because of the less forbidden energy gap, and also it is a indirect band gap it's a direct band gap semiconductor. Let me please excuse me for a couple of minutes. Okay, coming back. So let's move to the next question on gallium. In a gallium arsenide n-type specimen, the current generated is constant irrespective of the electric field. Please read it as field applied to the specimen. So you can relate to the gun diode working when you try to answer this question. Is the current generated constant? I mean, how much ever electric field you apply, is it the current remaining constant? Remember the case of a simple working principle or the work operation of a gun diode. As you apply the electric field, what will happen? So you know that when the electric field is applied, and suppose if the electric field reaches a threshold, say ETH or something like that, so the current will suddenly become oscillatory. Okay, and that is, I mean, oscillatory in the sense with respect to time. And that is microwave oscillation. I mean, frequency, the oscillations are in the range of microwave frequency. And that is called as the gun effect. Okay. So the current generated cannot remain constant irrespective of the electric field. So this is a false statement. Okay, I hope it's clear. Okay, now coming to the fourth question. When the electric field applied to the gallium arsenide specimen, so whenever we say gallium arsenide specimen, basically it's the gun diode itself. So you can just think of that way. is less than the threshold electric field. So we are looking at a case when E less than ETH. Okay. Whenever electric field is less than the threshold, how is the current? Is it increasing linearly? Is it decreasing linearly? Is it increasing exponentially? Or is it decreasing exponentially? To answer that question, you can think what happens when the electric field is less than the threshold, or how the electrons behavior is. So whenever this electric field is increasing, basically the electrons will try to jump from the valence band to the primary value of the conduction band. So basically the current will increase linearly. Yes, your answer is right. Yes, the current will increase linearly. Okay, now we have a question here. When the applied electric field exceeds the threshold, so that means E greater than ETH, the electrons absorb more energy from the field. So basically electrons are absorbing energy from this applied electric field. Okay, and it becomes hot electrons, cold electrons, emission electrons, none of the above. Emission electrons. Okay. So the right option is not emission electrons, it is hot electrons. So basically, once the energy is being absorbed, it tries to be the hot electrons. But as you know, I mean, it is trying to jump from the valence band to the conduction band's secondary valley. Okay. Uh, but then the mobility reduces. Okay, so that is why we call it as hot electrons. Now, coming to the next question, gallium arsenide is used in fabricating gun diode. So gun diode is a bulk device. Is it a sliced device or made of different type of semiconductor layers? What do you think? So you know that gun diode is made of a gallium arsenide. So is it a bulk device? So you know that it's a pure semiconductor. I mean N-type gallium arsenide. There are no semiconducting layers. Okay, that's the main point to understand about gun diode. So basically there are no different types of semiconductor layers in case of a gun diode. Gun diode is just a pure N-type gallium arsenide. So that will exhibit the gun effect. Okay, so that is a bulk device. Okay, it does not have any different layers, or it is not a sliced device. So it is a bulk device. Okay. Okay, then now we have a small numerical right here. Probably you can try this out. In a gun diode oscillator, the electron drift velocity is 10 power 7 centimeter per second. And the effective length, okay, you know the length, effective length is L equal to 20 micrometers. What is the intrinsic frequency? Can you calculate? Try calculating this. So the intrinsic frequency equation is Vd by L. So 10 power 7 centimeters. So centimeter per second, we can make it 10 power minus 2. and then 20 into 10 power minus 6. So the answer is 5 gigahertz. Yes, as you all got the right answer, it's 5 gigahertz. So the equation for the intrinsic frequency, or the frequency of oscillation, is the drift velocity divided by the effective length. Okay, so now we have a question here. Now we will try to. So now we will just. Okay, before moving to the question, I hope this is. This graph of operation of gun diode is just familiar to all of you. So as you see, it's a graph between the applied electric field and electron velocity Vt. So as the applied electric field is increased, the electron velocity is also increased. Okay, so it's a linear behavior till the electric field reaches threshold, and then you have a negative differential resistance. So if you notice, this is the negative differential resistance region, wherein you have this gun diode act as an oscillator. Okay, so that is about the gun diode, and you know the basic working principle of gun diode. So I just wanted to make a note of that. Okay, so now let's move on to solving a few questions which will eventually help you with solving the assignment questions. So the question is on Schottky diode. And before going to the question, let me discuss what is the diode current equation. So ID, diode current ID is IS, that is the saturation current, e raised to V by eta Vt minus 1. Or you can also write it as Is into e raised to alpha times V minus 1. So here please note that alpha is 1 by eta Vt. And you know what is Vt? Vt is basically Kt by Q. And we have at the room temperature, we have the value for this. This is 25 millivolt. Okay, at room temperature. Okay, so and eta is the ideality factor. Eta is the ideality factor, and V is the applied voltage. Okay, V is the applied voltage. Okay, so let us go to the question once. Okay, so you are given that the saturation current is 0.1 nanoamperes. Ideality factor is 1.1, that is eta, and Kt by Q is nothing but Vt, which is 25 millivolt. If the diode current, that is ID, is 2 milliampere, what is the applied voltage across the diode? Can you calculate the applied voltage across the diode? So use this equation. You know what is ID, you know what is IS, eta is known, Vt is known. So the only parameter which is unknown is V, which is the applied voltage. Okay, so let us try to substitute 0.1 nanoamperes, 0.1 into 10 power minus 9 IS. Oh, sorry. So basically you have 2 milliampere is equal to. So that is the diode current. Now saturation current, which is very small, which is 0.1 nanoamperes. Okay. E raised to V by eta is 1.1 into Vt is 0.025. 0.025. Okay. Minus 1. Can you, I request everyone to try. Here we have an answer. Let's cross verify if we all of us are getting the same answer. Once you get the answers, I request you to type in the chat. We'll wait for everyone to just try, give it a try. Point 0.0275 is 0.0275 is not the right answer. Please do try again. So once you reach this step, you have to just take ln on both sides. Ln on both sides. Then you should be getting the value of voltage to be 0.462 volt. Yes, right answer. So I hope this question is clear. If you have any doubts, please ask, or we'll move on to the next question. we'll try to discuss the next question. So this is again a question on Schottky diode. So a modulating signal of frequency 2 kilohertz and amplitude of 10 millivolt. Amplitude modulates a carrier having a frequency 1 gigahertz and amplitude 50 millivolt. The modulated signal is detected with a Schottky diode having Kt by Q 25 millivolt. So basically a Schottky diode is being used as a detector. So you have a modulated signal which is an amplitude modulated RF carrier. So if you have a Schottky diode plus then you have a module which is an LPF, basically the low pass filtering and DC removal, say removing the DC component, and you get a, you try to, so once you, so here your input is your modulated signal. From that modulated signal you are recovering the message signal. Okay, so if you look at the question, what is given is a modulating signal of 2 kilohertz. So basically this is FM and this is the amplitude of the modulating signal, AM, or maybe we can denote it as VM, whichever is convenient for you. Modulates a carrier. So this is the FC. Carrier is 1 gigahertz. Okay. Then the amplitude of the carrier is 50 millivolts. So let me make it as VC. Okay. The modulated signal is detected with the Schottky diode. So after low pass filter and DC removal, amplitude of the detected current. So the question is about the current at the output of this module. I mean output after the low pass filter and the DC removal. So assume the ideality factor like eta as 1, unity, okay, and the junction resistance is 4 ohms, okay. So to before solving this question, I have something to just make a note of this. So you know what is the output of this? So it should be V naught square GD dash by 2 M cos omega mt. Okay. So as per this, so V naught is basically the applied V naught is basically the carrier amplitude, and GD or GD dash. Okay, let me first tell you what is GD. GD is basically 1 by RJ. I mean, inverse of the resistance is the conductance. So basically the dynamic conductance. Okay, 1 by RJ. So here you, in this equation, you have something called as GD dash. Okay, GD dash is alpha times GD. I hope you remember what is alpha. In the previous question, I had told you alpha is 1 by eta Vt. Okay, into GD. So here eta is taken as 1, ideality factor. So this reduces to be GD by Vt. Okay, so that is your GD dash. Now, what is in this equation? M is the modulation index. Okay, here if you so I hope you remember what is modulation index. Can you tell what will be the value of modulation index in this particular question? You have the amplitude of modulating signal and also the amplitude of the carrier signal. Yes, right answer, it is 10 by 50, which is 1 by 5. Okay, so M is 10 by 50, which is 0.2. Okay, basically M is Vm by Vc. Okay, so now which is 0.2. Yes, right answer. Okay, now try to calculate. So assume uh, so we are looking only at the amplitude of the detector current. Okay, so the amplitude is basically what I naught is V naught square GD dash M by 2. Cos omega mt, you can take it to be whenever it is maximum. Okay. What is V naught? V naught is the carrier amplitude. So now can you try calculating this? So let me just tell you this GD is 1 by RJ 1 by 4, which is 0.25. Multiply that with alpha, you will get GD dash. So GD dash is GD by VT. So 0.25 by 0.025. Any answers here? Okay, you have the final answer, right? That is 2.5. Yes, right answer. It's 2.5 milliampere. So as I said, take 50 millivolt square into GD dash is 10 into modulation index is 0.2 by 2. Okay, so the final answer, once you solve, you will get it as 2.5 milliampere. I hope this question is clear. If there are any doubts, please ask. Okay. So now let's move to another question. So for this question, so you have a question based on PIN diode. PIN diode is used as a series switch, has a parasitic inductance. Say the inductance value is 1 nanohenry. The operating frequency is 1 gigahertz. Considering the Z0 for the line segment as 50 ohms. So this is 1 gigahertz. This is Z0 is 50 ohm. So the insertion loss for the switch under on condition. So whenever the switch is on, the insertion loss is 0.4 dB. Okay. Find the closest value of series resistance of the diode. Okay. So let's think about a pin diode used as a series switch. Okay. Suppose you have a source voltage and line impedance which is Z0. So this is taken as 2V0 and this is the diode. So diode impedance is ZD. Okay, the pin diode. Then suppose you have a load which is basically say Z0. So this is the configuration of a series switch. Okay, pin diode being used as a series switch. Now taking VL, that means the low voltage across the load. Okay, how do we take VL? VL is 2V0, that is a source voltage, multiplied by Z0 divided by 2Z0 plus ZD. Okay, so that is the load voltage. Now, how do you calculate the insertion loss? So, insertion loss is minus 20 log of VL by V0. Okay, minus 20 log of VL by V0. So 2Z0 by 2Z0 plus ZD. So that is insertion loss. Now what is ZD? So ZD is the diode impedance which will depend on the diode's equivalent circuit. If you remember, so the diode has an inductance, a capacitance and then a series resistance. So this is RS, L and CJ. Okay. So in as per the question, you already have the value of RS. Okay. RS and you okay, whenever it is used as a series switch, you have only these two, RS and L. Okay, so the final equivalent impedance of the diode can be written as RS plus J omega L. Okay, so RS is not known to us. J into omega is 2 pi F. F is 1 gigahertz, 10 power 9. L is 1 nanohenry. So that is again 10 power minus 9. So this gets cancelled and finally the impedance is RS plus J 2 pi. Okay. RS plus J 2 pi is ZD. Now you are given with the insertion loss value. Okay. 0.4 dB. You have a 0.4 dB loss. So equate that to minus 20 log of 2Z0. So that becomes 2 into 50 becomes 100. 100 plus RS plus J 2 pi. Now can you simplify this and find the answer for this RS, which is the series resistance in the equivalent circuit of this diode. I request everyone to try this. And find out the value of RS. Just taking a couple of minutes to give everyone a time to find out this. I hope everyone will try. Hello, have you got any answers? Maybe you will get uh, a quadratic equation which might have yes, so answer is 6.58. Yeah. Anybody else with the answers? So, as nobody else is responding, I think I request you to verify once again because I am getting an answer of 4.52 as the closest, I mean, the series resistance value. Uh, just please cross verify. I request everyone to again check back if it is maybe it's 6.58 or 4.52. I'm getting an answer 4.52. Any doubts in this question? Okay, let's move to another question here. Um, okay, so now we have a question on a varactor diode having a parameter gamma as zero point 0.5 and V naught. So take this as V naught. It's 0.5 volt. Given that the junction capacitance, say C naught, okay, junction capacitance of the diode C naught is 20 picofarad when there is no reverse bias applied. Okay, whenever there is no reverse bias, you have C naught equal to 20 picofarad. Then for a reverse bias voltage of 10 volt, what is the capacitance? Cj. Okay. So you have the fundamental equation for Cj. You know about the varactor diode as I told before. Based on the applied voltage, the capacitance, the junction capacitance will have a change. Okay. So Cj is a function of V. So how the equation if you write Cj of V is equal to C naught by 1 minus Vr by V naught the whole raised to gamma. Okay. So because Vr is the reverse bias voltage, say taking this reverse bias of 10 volt, you have to take minus 10. So this becomes plus. So C naught is already in the question 20 picofarad. 20 picofarad by 1 plus Vr is the minus minus. So this is 10 divided by V naught. So V naught is given in the question 0.5 raised to gamma. Gamma is the diode parameter which is 0.5. Okay. So final answer for the capacitance needs to be calculated. You know picofarad to be taken as 10 power minus 12. I request everyone to work out this. So answer is 3.645 picofarad. Huh? Okay, let me just confirm. Anybody else with the answers? It's a simple question. Ideally, I think everybody should be able to solve this. It's a very simple question because direct formula, we're just applying the direct formula. So yes, your right answer is 3.654 picofarad.
Hello, madam.
Yes.
Madam, last problem, I don't know how to take that log, madam. I forgot the 0.41, so tell madam.
Are you talking about the last question or this
Yes,
question?
ma'am, that 0.4 g is equal to minus 20 log of something is there, no, madam.
Yes. Okay.
After that, I don't know how to simplify, madam.
Okay. You should have asked before. So this is a modulus, if you have noticed.
Modulus.
Okay.
Okay,
So
madam.
in that, if you take the modulus of how do you take the modulus of a complex number? You have to think about that. So 100 is a real number. That's fine. So in the denominator, it is square root of 100 plus rs the whole square plus 2 pi the whole square. Okay. So this
Okay,
will
madam.
be minus 20 log of this. Okay. Is
Okay.
equal to 0.4. Now you know how to take the logarithmic base. So 10, that will be 10 power minus 0.4 by 20. Is that clear or should I write it down?
You write, madam, that last step.
Okay, last step would be 10 power minus 0.4 by 20. Okay, you take 20 minus 20 to the other side. So 0.4 by 20. Now you take the logarithmic, the inverse logarithmic. So it will become 10 power minus 0.4 by 20. Is that clear?
Yes, madam.
Okay, so then equate it to 100 by square root of 100 plus r is the whole square plus 4 pi square. Okay. Now take square on both the sides. Okay. Now if you take square on both the sides, so this square root on the denominator will go. Okay.
Cancel.
Yeah. So now this equation will have rs square. So it will be like a quadratic equation. Final equation will be a quadratic equation with rs square, rs and a constant value. So
okay, madam. Hereafter I will do, madam.
Then you can just solve the equation, the quadratic equation. In the calculator,
okay,
in the calculator, you can just type in the coefficients.
That equation mode, no, madam.
Equation mode. Yes, exactly.
That I know, madam. One day you
Okay,
teach
fine.
in class.
Okay.
Okay,
So
thank you, madam.
you can try RS. So are there any other doubts? Because it is 7:30, I would like to ask you, like, if you have any particular doubts in the previous assignments or any this part of the assignment or just general doubts in any of the topics.
Madam, last week that last two problem, madam, that the low pass filter is there, no, madam. That problem only I need answers, madam. Remaining all okay, madam. The last week that low pass filter that order is two. How to something is there, madam. That seventh question, madam.
Okay. So
That
assignment question or the one which I discussed in the session?
no, madam. Assignment questions last week 6, madam.
Okay, okay.
Assignment.
Assignment question. Okay, you are referring to the assignment question. Okay, fine, fine.
Yes, madam.
Just a minute, I'll take out that question. Okay, so the order of the filter is given in the question, right? The order is second order, and it's a low pass filter with a cutoff frequency of 1.5 gigahertz. Source impedance is also given. Value of the inductance to be used in the low pass filter. So that is a similar question which I have discussed in the session also.
I think another question. Otherwise, I will check. I will send mail, madam. The questions.
Okay, okay, fine, fine, fine.
Okay, I think
Because
another
it,
question
it
I
is
will
the
take, madam.
same, similar question had been discussed in the session also.
Okay,
Okay,
madam. I will check,
okay,
madam. I think another questions.
okay, fine. So if there are no doubts, I have one more question in my question bag. Like, we'll just finish that question, and if you have any other doubts, you can ask. So the last question is, for a BJT, the operating in the microwave frequency range, the unity gain frequency FT is 30 gigahertz. Short circuit current gain of the transistor at 2 gigahertz. So FT is called as the unity gain frequency. Okay. So you should know the expression for FT. FT is GM divided by 2 pi C pi. So this is with reference to the equivalent circuit model of a BJT. Okay. Please refer to that. I am not going to discuss all that here. Now, so the FT equation is should be known to you, and the other thing is the short circuit current gain. So how do we write the current equation for current gain? So current gain equation is given by, so basically it's the ratio of output to input current. Okay. So once you solve it, you will get it as Gm by C pi divided by omega. Okay. So if you know these expressions, this question is very simple to solve. Okay. So the unity gain frequency is given, which is basically Gm by 2 pi C pi Ft okay, is equal to 30 gigahertz. Now, what is Gm by C pi? From here, I can write 30 into 2 pi. So, 60 pi into 10 power 9. Okay. Now, coming back to the expression for short circuit current. So, you need to calculate the short circuit current gain at a frequency 2 gigahertz. So, this omega you have to replace with 2 pi f, where f is the operating frequency 2 gigahertz. So, AI is Gm by C pi is 60 pi into 10 power 9 divided by omega is 2 pi f. F is the operating frequency 2 gigahertz, 2 into 10 power 9. So once you solve this, what will be the short circuit current gain? Yes, so the right option it's 50. Okay. So if there are any other doubts, you can ask at this time. So the session is open for question answers if you have any doubts.